In problem 29.65, you can see that there is a rectangular loop on the right and has a length L and has a slide wire with mass M. That's the slide wire is this thing right there. Okay. And there's a uniform magnetic field B, and we're going to slide the slide wire to the right with some force. It's going to keep a constant speed. Okay, and then we're going to hold on to that speed. We want to know what the force is that's required to do that. Well, in other words, if we look at the force diagram of this thing, maybe, okay. If we look at the force diagram, this is just of the bar itself. Okay, it's going to have a forward force, whatever forward force I put on it, maybe. And that forward force is going to be countered by the backward force from the magnetic field, the Lorentz force that acts on it. Okay. And that Lorentz force is going to be due to and why would there be a Lorentz force? Because there's going to be an induced current that happens inside that wire, okay, due to the voltage that's going to be created inside there. And if we look at it, which means that that force is going to be the same as FB, which is going to be BIL. If you look at the problem, the text, they start to call it A magically all of a sudden. Like if you look at the answer at the end, it's in A, okay, but the answer should be L, okay, because that's what's in the picture. So if you look at it, first we're going to have the B and the L are constants. The only thing that is unusual here really is I. Okay, and the I comes from the induced voltage. So it's going to be the induced voltage divided by the resistance. And where did that induced voltage come from? Well, it came from a change in the, so let's talk a little about that over here. According to Faraday's law, and again, we're just looking at the magnitude of it. It's going to be the change in the magnetic flux. It's a terrible phi there. Okay. In this case, it's not going to be the magnetic field that's changing. It's going to be the area that's changing. I should put a bar there like that. So it's the area that's changing. One of the dimensions is not going to change at all. The L is not going to change this dimension along this way. Okay. So that area you can see is getting bigger and bigger as the bar moves this way. Okay. But one dimension is not going to change at all. It's only the X one that's going to change. Sorry, I'm going to erase that. It's not dx really. We're just going to call it delta. It makes more sense. Which is going to be that velocity that's already written up there. So, oops, let me erase that. Okay. So we're in place with velocity, so it's going to be B times the length times the V. So that means that that force is going to be, it's going to be B times L times BLV all over R. We gather all those terms together, we get V B squared L squared over R. And that's the amount of force we're going to have to drag it forward at that constant speed V, whatever speed it is. In part B, they ask us to find the distance that it goes, the distance x, that it slides before coming to rest. So it's going to start at that speed v0, and we're going to end, obviously, at 0. As it slides to the right and comes to a stop, we're going to have a force diagram where our forward force is gone now because we've released it. And we're going to just have that F sub B. The only problem we have is that that arrow is going to get smaller and smaller as it goes, so we can't just calculate that and find out how far it goes or any of that. So I think the easiest way to do it turns out to be that we go ahead and calculate. First, we're going to find the acceleration of it. So A equals that force divided by the mass, so it's going to be, which we found earlier in part A, is V B squared over L squared over M, because it's going to be the force divided by the mass, and we've got an R in there also. Okay, which we're going to rewrite as dV dt equals V B squared L squared over MR. And it's going to be negative. I should point that out because it is acting in the opposite direction. Okay. And we're going to separate everything out. Unfortunately, we're going to have to actually do this as a differential and separate it into separate pages or separate variables. So I'm going to take all the V's and move them to one side. So I'm going to have dV over V equals whatever's left, which is negative B squared L squared over MR dt. Okay. And we have to integrate both sides too. So this integral is going to be from 0 to t, and this integral is actually going to be from V naught, because it doesn't start at 0, to V. So we're not going to put 0 in yet. We're just going to integrate those. Okay. So the integral of the other side is going to be ln. So it's going to be the natural log of V over V naught, natural log of V minus the natural log of V naught, which is going to end up being V over V naught. And this is all just going to be negative B squared L squared over M R all times T. Okay. We're going to take each side, take e to the each side to get rid of that ln, and we're going to have an expression that says V over V naught equals e to all that stuff, negative B squared L squared over M R times T. Okay. Which means we're going to end up with a V equals V naught e to the negative B squared L squared T over MR. And that makes sense. Like at t equals 0, we're going to get V naught. It's going to get smaller as it goes. And then we're going to end up with, when t is very, very big, V is going to be 0. Okay. But that doesn't give us the position. We're going to actually have to take the integral of that as a function of time to find out what the positions are, which we're going to have to clear a page to do. Okay, now we have an expression for that. So to find x, we're going to have to take the integral of that with respect to time. And that's not the worst integral in the world. It has 8,000 terms, but it's not the worst integral going in the world. So it's going to be x equals, and again from 0 to t. Okay. And it's going to be a V naught e to the negative B squared L squared T over MR. Okay. dt. Okay. Well, obviously the V naught is just a constant. Okay. And the integral of an e function is just going to be that function divided by the constant or the coefficient inside of the function. So it's going to be, let's do it. Okay, well, this is yeah, no, that's fine. That's right. So it's going to be V naught e to the negative B squared L squared t to the m r all divided by negative b squared L squared over m r. Okay, so we can actually straighten that, and that's all going to be evaluated from 0 to t. Technically, it's going to be evaluated from 0 to infinity because we're going to look at like a really, really long time. So let's plug all that stuff in. So it's x is going to be, we'll move everything around. So it's going to be negative m r over, actually it's going to be a v naught because that's constant, and a b squared L squared. That's going to be on the bottom there. And then we're going to have e to the negative b squared L squared t over m r. And again, we've not evaluated it from basically we're going to evaluate it from 0 to infinity. Okay, so that actually doesn't turn out to be too bad. Okay, because e to the infinity is going to be really, really large. Okay, and e to the negative infinity is going to be really, really small. So that means that that's going to actually be 0. That's going to be minus all of our other stuff, okay, which is going to be e to the, make sure we have this right, okay, which is going to be, if I put 0 in there, it's going to be e to the negative 0, which is going to be 1. That's going to be times, or negative, it's going to be times a negative 1 because it's going to be like that. It's going to be times negative 1. And the whole thing is going to be times m r v naught over b squared L squared. Okay. And that's the way it turns out, actually. It turns out to be, that's the exact answer that you're given. Notice again that they give a squared in the answer because apparently they just couldn't keep track of whether it was a or L when they were making the answer. But that looks right.